This is our lecture video in fluid mechanics under the topic Hydrostatic Force on Plane Areas. Now this is the continuation of our discussion. This is the part 2 wherein we will solve the sample problems number 4 and number 5. So in this example, number 4, it is special because we are dealing with more than one liquid. We have here the gate given in the figure. It is 1.5 meter wide. It is hinged at point M and it is resting against a wall, a smooth wall at N. Determine the following. First one, the total hydrostatic force acting on the gate, and letter B, its line of action from the bottom. Okay, so first we will solve for the hydrostatic force acting on the gate. As we have solved from the first video, when we are dealing with inclined surface here, the force therefore acts perpendicularly to that surface. So here is our hydrostatic force, and it's located at its center of pressure. So this is the center of pressure. Now, the thing that is special here is we're dealing with more than one liquid. We are dealing with oil with a specific gravity of 0.85 and seawater with a specific gravity of 1.03. Given the height of its liquid, how do we solve now the hydrostatic force? So, first and foremost, we need to get the area of this wall. The problem only gave us the width, which is the 1.5 meter. So we need to solve for the height or the length of the gate. So this is our gate. So we have given the width of 1.5 meter. So what is the length? So we will solve for the length by getting the square root of 2 meters. So this one here, 2 meters and 2.5. So it's a triangle. So 2 squared plus 2.5 squared. So square root of 2 squared plus 2.5 squared. So that is 3.2 meters. 3.2 meters. Okay, now let's go to the force. The formula for the hydrostatic force is equal to the unit weight of the liquid wherein the object or the plane is being submerged multiplied with the HC, or the vertical distance from the surface of the liquid up to the center of gravity of the object, of the submerged object, and then the area of the submerged object. So how about this one? How do we solve that if we're dealing with two liquids? First, we need the pressure. So we need to compute for the total pressure that is pressing on the gate. So to get the total pressure here, we need the pressure of oil and the pressure of the seawater that is acting on it. So first, we need the unit weight of oil. Unit weight of oil is equal to 0.85 times the standard unit weight of water, 9.81. And then the height. So what's the height of the liquid? That is 2 meters. So that's the first pressure The second pressure here is the seawater, and the unit weight of seawater is 1.03 multiplied with 9.81. And how about how do we compute now here the height? We need to compute it from the surface of the seawater up to the center of gravity. So where is the center of gravity of the gate? So it's located here. CG is located here. So this height here, and that is equal to 4 plus 2 divided by 2. Okay, so that's the total pressure acting on the gate. Now, in order to convert it into force, we need the HC, or the area, should say the area, multiplied with the area. So this is already the gamma HC, and then this part here is the area, and the area is 1.5 times 3.2. Okay, so what's the answer here? 0.85 times 9.81 times 2 plus 1.03 times 9.81 times 5 times 1.5 times 3.2. And the answer here, the force here is 322.55 kilonewton. So that's the force acting on the gate. How about B? What is being asked on B is the line of action from the bottom. So line of action from the bottom. So it's looking for the since it is inclined, so we can assume that it's looking for the Y here that is also inclined. So it's line of action from the bottom. So we are solving for Y that is inclined. Okay? So how do we solve for that? So Y here, if you observe it, so if this is your point, the eccentricity E, so Y now here is equal to 3.2 minus E, or the eccentricity E. Now we need to solve for eccentricity E, that is I sub G, or that is the moment of inertia, divided by the area, and the YC. YC because we are dealing with inclined surface. So here is the YC. So from the center of gravity, center of gravity up to the. Now we cannot pinpoint here which surface, right? So we need to find the value of HC in order to get the value for YC. Why? Because of the triangle that is being formed. This is your HC. From from our first video, we already showed there the relationship of HC and YC, and they form a triangle. So we have here HC, and this is your YC, and this is the theta that is being formed. Now this theta here is the same with the theta at the inclination of the gate. So we can now solve for the value of theta. So for the value of theta, we have here tangent theta is equal to D. So this is the triangle that is being formed. Take note. That's the triangle. So the opposite here is 2 meters divided by the adjacent of 2.5 meters. So theta now is equal to inverse tangent of 2 over 2.5. So that is 38.66. 38.66 degrees. And we can now find the value of HC by using the total hydrostatic force that we were able to solve in letter A. So F is equal to gamma HCA. How about the unit weight? What unit weight are we going to use? We will going to use the unit weight where our submerged object touches. So from these two liquid oil and seawater, the liquid that is being touched by our gate here is the seawater. Therefore, we will use the unit weight of seawater here. So using the total hydrostatic force 3.22.55, using the unit weight of seawater, which is 1.03 times 9.81, compute for HC. Then we have here the area of the gate. Area of the gate is 1.5 times 3.2. We now have here the value for HC. 322.55 divided by 1.03 times 9.81 times 1.5 times 3.2. So HC is 6.65 meter. Now we have our HC. We can now solve for YC using this triangle. So that is sine theta or sine 38. Oh yeah. So it's sine theta is equal to HC over YC. So we have sine of 38.66 equals HC 6.65 divided by YC. YC now is equal to so that is 10.645 meters. Okay? So finally, we can now solve for the eccentricity E. So E is equal to, that is the base 1.5, the height of the gate, which is 3.2. So 1.5, 3.2 raised to 3 divided by 12 all over the area, 1.5, 3.2 times the YC, which is 10.645. So we now have the value for E. So the value for E is equal to 0.08 meter. And then we can now use this E here in order to get the value of Y. So Y now is equal to 3.2 divided by 2 minus E. That is 3.2 divided by 2 minus 0.08, and that is now equal to 1.52 meter. So that 1.52 is the line of action from the bottom. So this part here. Okay, so that's example number 4. Now let's go to the last example, number 5. We have here a vertical plate that is submerged in water. So this is water surface. Find the magnitude of the hydrostatic force on one side and the depth to the center of pressure. So the total hydrostatic force, we're looking for it, and the depth to the center of pressure. Now, how do we deal with this irregular shape? So we need to divide it into regular shapes. So to divide it into regular shapes, we can see here two rectangles. So this is our area 1 and then area 2. This is the center of gravity for area 1, and this is the center of pressure for area 1. Then this is the center of gravity for area 2 and center of pressure for area 2. Now let's solve for the forces of these areas, okay, separately. So we need to find the first force, that is force sub 1, F1, that is gamma. So they have the same gamma because they're both submerged in water. So gamma HC1 area 1, and that is equal to 9.81. So 9.81 times the HC. So what is the HC of area 1? So it's from the surface up to the center of gravity. So this is the HC1. And for the HC2 here, from the surface up to the center of gravity. If for HC1, we can have here 2 plus that is 7 divided by 2 times the area, which is 3 by 7. Okay, that is for F1. So let's put that here. For F2, F sub 2, we have here gamma of water, HC2, and then area 2. So we have here 9.81, 2 plus, and that is, so HC2 is, so that is 2 plus, this is actually 3 meters here. 2 plus 3 plus 4 divided by 2, and then the area, which is, so this becomes 2 meters. It's 2 by 4. Okay, let's now solve for the forces. So this is 113.0555. 1133.055 kilonewton. And this one here, so this is 549.36 kilonewton. Therefore, the total now, so for letter A, F total is equal to F1 plus F2, and that is equal to 1682.4. That's for letter E. For letter B, it's looking for the depth to the center of pressure. So to find the depth of the center of pressure, for the center of pressure, we have here F total, H at the center of pressure is equal to F sub 1, H center of pressure 1 plus F sub 2 center of pressure 2. Okay? So we need to find the center of pressures here separately. So the center of pressure here separately. How? We need first the values for the eccentricity 1 and then the eccentricity 2. So let's solve for the eccentricity first. For the first one, the E1, so E sub 1, we have here the area. The area here is 3 by 7 raised to 3 divided by 12. Then the area, and then HC. The HC here is 2 plus 7 divided by 2. So that is E1. And then for E sub 2, E sub 2 is this one here. That is 2 by the height of 4 meters raised to 3 divided by 12. The area 2 by 4 times the HC. The HC here is 2 plus 3 plus 4 over 2. So what's the value for E? So the first one, .74, 0.74 meter. And then for E sub 2, we have 0.19 meter. Okay, therefore, our HCP now, HCP1 is equal to 2. So HCP1 is, we have here HC1 plus E, right? Our HC1 here is 2 plus 7. HCP2 is HC2 plus E sub. That is 2 plus 3 plus 4 divided by 2 plus 0.19. So 6.24 meters. Then the other one is 7.19 meters. Therefore, we can now substitute E in this formula. F total, what's our F total? 1682.4. HCP equals F1, our F1 here, 0.55, 6.24 plus 549.36 times 7.19. Okay, so we can now have the value for HCP is equal to 6.55 meters. Okay. So that's the depth to the center of pressure. So that's the example number 5. Okay, so that's all for this video.